Everything you need to do is on the web, although I have to tell you, this is the second time I've taught this course, and the first time was 4 years ago. So, that means A, I don't remember anything, and B, it's obsolete anyway. So, I'm willing to negotiate with you on what the content of the course should be. It's a small group, so we can afford to negotiate. What I think we should do, what I did last time was to have 4 or 5 rather heavy labs, 2-week labs, and then a final evaluation, which was a oral presentation. So everybody in the class gave a presentation on some topic related to the class. There has to be some sort of final evaluation that's part of Cornell's policy. I don't want to give you a final test, although I would consider it if that's what everybody requested. I would also consider, instead of a final talk, a project, if you want to do lab work. So, anybody have any feelings about this? You want to, Amrit would like a project. All projects. How many people would love a final? Let me tell you how I would do the final. It would be a 1-week take-home. Design project. Paper only. Nobody wants that. Talk about suck your brains out for a week. Okay. So the final's out. How many people would prefer a final talk? More labs, but then a shorter final. You prefer a final talk.
Can you elaborate on that? When you say more labs, that sounds good.
All right. So if we're going to do a, that might be record short. If we're going to do a final project, there's going to be about 5 weeks at the end of the semester where you do the final project. If we don't do a final project, there's going to be more assigned labs to fill in that 5 weeks, and then there will be a final talk. I prefer the project because it gives people more region for creativity. Some people prefer a final talk. Those tend to be more kind of canned because it's library work and there's not as much creativity that goes into it. Okay, let's have show of hands. Project. Final talk. Wait a minute, Akshay. You're taking the course also? Is that right?
Yeah.
Okay, Akshay is also the TA. Stand up, take a bow. So, and nobody wants a final exam, right? Okay, it's going to be a final project then. That means I may edit the existing list of lab exercises, change it up a bit. Final project I will assume for this class, as a graduate level class, that you will sometime before the last 5 weeks, we'll figure it out in a couple of weeks. Sometime before the last 5 weeks, you'll come up with a proposal for what you're going to do for a final project as a group. I mean, it can be groups of 2 or 3 people. And that should be based on primary literature. So I want you to go off and read some original scientific papers on whatever you decide to do your work on, and then implement some piece of what you read out of the primary literature. So I want more depth than, sucking up a Wikipedia article And I want some reference data. Range of projects that I think would be possible in this class is rather wide. I think there could be more mathematical projects, which are more MATLAB simulation kind of things. There could be straight up analog electronics. There could be some more work on infrared brain scanners. To reference a project from 4760. But in that case, I want to see some more sort of theoretical basis of why it should work and how it should work. So now I need to get some idea of background here, because this is kind of partly biology and it's partly electronics. So how many people are ECE? Ooh. And you are BME? Mechanical. Mechanical? Wait, you're flat out bio, right? Bioengineering. And you're mechanical, but you've done a lot of electrical engineering. Yeah, something like that. Okay. When's the last time, when's the last time you took a biology course? Never? How many people? Never? High school? Oh dear. College? Okay, so a few have had high school biology or college biology. That says I better do a little bit of biological review here to kind of kickstart stuff. There's also some biological references on the 5030 page. How many people could walk up here and draw me a non-inverting op-amp circuit? Non-inverting op-amp amplifier. Hold up your hand. Okay. If you've never handled an op-amp before, you've never drawn yourself a schematic, think carefully about whether you want to take this course or not. Because I'm going to assume that given a block diagram of a circuit, that you can generate the detailed schematic and build the circuit. Now, obviously we're going to help you with this, and part of the exercise is going to be taking a series of data sheets for the various components and interpreting those data sheets into a circuit. In some ways it's straightforward, in other ways it's mind-bending, because data sheets don't seem to be written for human beings. They're for not normal human beings anyway. They're written for the engineer, by the engineer who designed the chip, for the engineer who designed the chip. What makes this extra interesting is that in this class we are going to record from ourselves, and that means that safety is paramount, which means that we're going to have to bend over backwards to build circuits that are safe, and that makes them more complicated, because there will be no electrical connection between you and the computer at all. So anything that goes between you and the computer is going to have to be on a light beam or a transformer, without an electrical connection, and you'll have to verify that there is no connection. So we're going to have to do a bunch of conversions back and forth across an isolation barrier. So let me tell you what I think the course is and what we're going to need for the course. And and then do some of the logistics, you know, grading and that kind of stuff. Then we'll get down to some content, because this is a 75-minute or 80-minute lecture. Let me tell you, it's easier to talk for 80 minutes than it is to listen for 80 minutes. So, I apologize in some ways, but since the other class is Monday, Wednesday, Friday, it makes more sense for me to lecture every day than to pile up lectures on Monday, Wednesday, Friday. So as you all know, we're electromechanical, chemical machines, and as are animals. And one way of studying how animals, including humans, work is to look at the electrical responses of animals. This is going to require some combination of sensors of various sorts, which we're going to play with this semester. And signal conditioning, typically amplifiers, filters, and so on, followed these days by a computer processing step. So we're going to be taking the general paradigm for this class is we're going to be building an analog front end, feeding it through an analog to digital converter, and then bumping it onto the desk machines in the lab, where the back-end processing will be done in MATLAB. So in terms of the lab work, we're going to have a combination of analog construction on the front end. The D-Day converter is given to you. It's a National Instruments device that MATLAB recognizes. I hope it recognizes it again this year. And then you'll be writing MATLAB programs to interpret the vectors of data that come out of the A to D converter. What we're going to need to make this make sense is some sort of electrical models of cells and biological systems. After all, it's an engineering course. So we have to be able to analyze the data, which means you have to have some sort of model of how the system operates. In this case, the system is you. And so we need reasonable being fairly realistic but also tractable models of how you work. What are you? What is your impedance? Let's say for a pacemaker, if you're going to design a pacemaker, you have to know what the impedance of the heart is. So you have to have some sort of electrical model of a heart before you can stick electrodes in there and expect to send pulses in which cause it to beat. So we need some sort of system for reasoning, for doing electrical reasoning about animals. We need some sort of electronic designs that are going to take now what we know about the animal, the impedance level, the voltage levels, and convert them into something that the computer can use. If you do a surface recording of electrocardiogram, you would expect to get maybe, class is closed. Don't be late. If you expect to do a recording of electrocardiogram, you might expect to get maybe 5 millivolts or 10 millivolts off the surface of your body if you put the electrodes optimally in various places. And the ADD converters we're using 5-volt ADD converters. If you want to get any kind of reasonable accuracy, you have to bump the signal up by a factor of 100 or 1,000 or so before you can expect to record. So there's going to be some analog step that matches the tissue electronics to the computer. There's another aspect of that which is probably not obvious at first thought, and that is currents in wires are carried by electrons, mobile electrons. Currents in your body are not carried by electrons. They're carried by mobile ions in solution. Electrons are not noticeably soluble in water. So there has to be a conversion somehow between the ions in fluid and the metal that is carrying electrons. And that's a non-trivial exercise to get that right. Although I have to tell you, on occasion I've recorded EEG by taking a piece of copper wire and duct taping it to my chest in 2 places. That works for a little while until the wire corrodes, or you get copper poisoning, or your chest turns green, or whatever. Also, duct tape really hurts when you pull it off, let me tell you. But in fact, virtually the only material that is suitable for recording from humans is silver chloride. And we'll talk about why. We have to talk about noise. There's all sorts of noise that come in from biological systems, plus many of the systems we're going to be recording from are rather high impedance. Whenever you have a high impedance, you have a high thermal noise implied by that impedance, because the noise in a thermal system goes as the square root of the resistance. So we need the hardware to to interface the two, and then of course we need the computer programs to implement whatever algorithms we're going to use for filtering or for classification. So I'm going to talk a little bit about basic biology, origin of electric potentials, electrical signals, tissue impedance. Talk about a little bit about MATLAB, because I suspect that most of you have used MATLAB as a scientific computing language for doing matrix operations or mathematical operations. You can build quite a nice graphic user interface in MATLAB, and I'm going to have you all do that, because if you're going to do any real scientific computing that's reusable, somebody else is going to have to use your damn program, and it better have an interface on it that's comprehensible. So we're going to have you build graphic user interfaces to everything you do in this class. The GUI interface is straightforward in MATLAB. It's just different than anything you've done before. How many of you have ever built a GUI in MATLAB? Okay, a few. Does this mean you tried and failed, or?
I had to like edit one time.
Okay. Okay, yeah. I have my own quirky way of building these, which I think is simpler. And we'll give you some examples of that. The DAQ interface, the data acquisition interface between National Instruments hardware and MATLAB, is unbelievably bloated. Now, like gigabyte. The image is huge. Using it is fairly straightforward. There are some interesting quirks. As soon as you instantiate the analog input device, you get, as a side effect, if you want, a hardware timer that allows you to schedule MATLAB events. That's really cool. You can do all kinds of periodic stuff. It becomes, at that point, it becomes a concurrent process. And you can shoot yourself in the foot with the concurrent process just like you can with any concurrency. So we'll have to talk about that a little bit. First lab will be MATLAB warm-up. We'll crank up the DAQ interface and MATLAB, and you'll play with the interfaces, get to know them a little bit before you actually have to hook them to some biology. And then, of course, we're going to talk about electronics. After all, ZCE, extracellular recording, intercellular recording, surface recording, waveform generation. I think my first guess for what the labs are going to be is introduction, as I said, to GUI and DAQ toolbox. Second one is going to be the tried and true plethysmograph. Have you all built that so far? Finger plethysmograph? Okay, the twist here is that I'm going to ask you to be able to record the pressure waveform from your finger, the blood pressure waveform from your finger, to then figure out a way of detecting periodicity on that signal, and when you have periodicity, to estimate the heart rate, but when you don't have periodicity, tell me that you don't have it. So you're going to have to make a judgment about the quality of the data on the fly, real-time quality of the data. Secondly, I'm going to ask you to implement a breath sensor, which is going to be a piece of stretchable material that is wired around your chest, so you can look at chest expansion. And to correlate the breath sensor with the blood pressure sensor, because when you breathe in, it lowers your thoracic pressure, which lowers the impedance to your heart and causes a larger stroke volume. When you exhale, it increases your intrathoracic pressure, it squeezes on your heart and lowers the stroke volume. So you get different waveforms of blood pressure depending on how you're breathing. You can turn off your heart for a beat with what's called the Valeslava maneuver. Have any of you know Valeslava and his maneuver? That's, you grunt. You pucker up everything and then you squeeze your abdomen. And it increases your intrathoracic pressure enough to cause you sometimes to skip a heartbeat. It also raises your blood pressure quite considerably. So you want to be careful about doing this because you can fall over. Third lab will be EMG plus force transducer. So I'm going to ask you to build an isolated electromyograph, put a couple of electrodes on your bicep or some other muscle in your forearm, record EMG, and to correlate it with a force sensor. I bought a bunch of force sensors. So if you were to put a force sensor on the bottom of the table and lift it up with your hand, you could instrument your bicep and directly correlate that with the force you were producing. You're going to have to calibrate the force sensors, probably using cans of beans or something, or kilogram weights, because they're fairly log linear, but not exact. Next lab, I'm willing to negotiate. What we did last time around 2009 was do skin impedance. Shoot a current through the skin, a few microamps into the skin, measure the voltage and then sweep the frequency and get the Bode plot of your skin. Remember Bode plot? Yes. Get the Bode plot of your skin. I'd be willing to do something else. Any ideas?
Can we skip electromyograph and replace it with EEG or something?
I will not let you record from your head or your body. Not as a first lab. I'm trying to make this redundantly safe. I mean, I want to make sure that you're recording from a peripheral place, which gives you one level of safety redundancy. You're going to be using low voltage, which gives you another level. And the third level is everything's going to be completely ground isolated so that you can get no current flows from this place to any place else in your body. And I want to keep all three levels of that, so I won't let you do EEG. If you want to do EEG as a final project, as a one-off, I'll consider it if you can convince me it's safe. I've had people do it in 4760 after they convinced me it was safe. Any ideas for a fourth lab that you would like to see rather than skin impedance? There was another lab I did last year, logically 4 years ago, which was to go out and get the database from, I think it was MIT, of cardiac waveforms, and write a heartbeat estimator for abnormal waveforms. That was kind of fun. Straight up math, not much instrumentation. Another possibility is a lab I used with freshmen 2 years ago. I would change it around for you somewhat, but the idea was that they built a model of the heart, an electrical model of the heart. Turns out that the basic mechanism of the action potential, which we're going to talk about in some detail. Is there a clock in this class anywhere? No. Okay. So the basic mechanism of the action potential is that a channel opens, a voltage-dependent channel opens and allows ions to go into the cell. The voltage dependency of that conductance change is exactly the same as the voltage dependency of a bipolar transistor for exactly the same reasons. It's a Boltzmann activation of a gap, of a voltage gap. And so bipolar transistors are a very good model for a channel, for a biological channel. So you can make a model heart out of 5 discrete transistors and some resistors and capacitors. You can actually make a model ventricle, then you need a model atrium, an SA node, and what we did with the freshmen was we had over a period of 3 weeks we had them build this and then make an SA block, which caused heart failure, and then brought it back to life with a pacemaker we had them build. And we could do that. Or some variant of that, which could be fun.
Can we model a heart and then build an external pacemaker to give the waveform?
Well, that's what this was. It was a model of a heart.
No, but with the external pacemaker.
It had an external pacemaker. So the pacemaker was a 555 timer, which some of you are probably familiar with. The Max 7555 from maxim-ic.com. maxim-ic.com. Max 755. By the way, these people are awesome. They'll sample anything you ask them for. They'll give you 3 anything and they send it by overnight. It is phenomenal. In 3 days you'll have parts. And the price is right. Max 755 is one of the most used integrated circuits in the world. A few 100 billion of them have been sold. The guy that invented them just died last year. They've been around for about 30 years. It's a basic timer module, and among other things, you can produce pulse train out of it. So it's a pacemaker. It's not low current. It's not anything you'd want to embed in you, but for use in the lab, it's really very handy to do. So we had them build a transistor-based, reasonable biological model of a heart, and then caused heart failure, and then brought it back to life with the sort of technological pulsar, which was the 7555. There's various things you could do. You could extend this to have a more realistic, say, calcium current. You could try and make the system more distributed than I did. I had a very lumped model of the heart. There's various things. You could each build a cell, and then the whole class could put them together to show conduction. What do you think? Shall we let that float for a while? That's lab 4. We can let that float for a while. Yes, we can let that float because I don't need to order any parts for that particularly that we don't use for lab 3. So we'll let that float. I had a great deal of fun with the heart model. I thought it was very entertaining. I had a great deal of fun with the freshman class because I asked you guys a question and you either sit there or you give me a very reasoned response. The freshmen, I ask a question, everybody has an opinion. Everybody has an opinion. Some better informed than others. But, you know, every question turned into a 15-minute discussion. It was fun. It was very fun. All right, let's do some logistics and grading and that kind of stuff. There's a highly recommended text, which is, I think it's at the campus store. Has anybody checked?
Yeah.
It's there?
It's there.
Good. I almost always check, but this year I didn't because my brain has been someplace else for 2 weeks. I, in general, think that textbook costs are obscene, and but this one is not so bad. What is the cost of this one?
I think it's $100.
$100. That's fairly low as things go. I don't want to know if you figure out some other way of finding it. So if we're going to do a final project, I'm going to have to modify this a little bit. But the general overall design is going to be 50% of the grade will depend on the 3 or 4 labs, and 50% of the grade will depend on the final project. It's usual kind of split for these big design courses. 25% of any given grade of any given lab depends on how well you work. 25% depends on the outcome, how complete was the demonstration of the project at the end of the assignment, and 50% depends on the write-up. This gives you a chance to recover from a project that exploded in your face, hopefully not literally. I have to tell one story. I was teaching a class like this over in neurobiology, introductory instrumentation, and half the people were biologists, half of them were engineers. One of the biologists was his first-year graduate student who was massive. He was a Texas state champion wrestler. He was built like a truck. But he'd had to stop wrestling because he had fairly severe back pain. He'd messed himself up. And so he was an unhappy guy because he was used to exercising heavily and he couldn't. And so he was kind of tensed up and grumpy, and the guy sitting next to him was this electrical engineer who kind of a little loose around the edges, and his partner, who was an Israeli trained commando, and the engineer blew up an op-amp, blew it right out of the solderless board and into the biologist's beard where it caught fire. His beard's smoking, right? And he sort of goes like this, and I see his shoulders bunch up, and I said, "Oh crap!" So I got behind him, ready to go. I figured I couldn't actually hold him, but I could sure as hell slow him down if I was hanging on his neck. Right? So I was going to get ready to push him back down in the chair, and the Israeli guy comes around, you know, and gets ready to go, and And the biologist sort of stood halfway up and then sat down and went, geez, put his beard out. And that was it. He blew up an op amp. It's so hard to do that. There's only one way I know of to blow up LM358, and that is to hook the power up backwards. And even then, it's fairly difficult to get it to go. Anyways, you can do works in lab groups of 2. I would prefer labs group of 2. If there's anybody who wants to work in a group of 3, I'll be okay with that as long as you scale the final project appropriately. Collaboration is encouraged within groups. You'll turn in one report. There's no homework. I assume that you're going to come to lab ready to go, otherwise you wouldn't be in this class. There's no homework. I'll help you with any questions you have. You have to read, the fact that there's no homework means that you have to read the labs early enough that you can come to class with questions. If you wait till the day before and you have a whole bunch of questions, you're going to get killed on the preparation piece of the lab, which is 25%. If you come in and say, gosh, I haven't looked at this lab yet, minus 25. Right? So, you work in groups of 2 or 3. You collaborate. Everybody should help everybody else in lab. I strongly believe the best way to learn something is to teach it. You should help each other. Help that is allowed is any verbal interaction. Here's how I did it. Here's how you should do it. That's fine. What's not allowed is you touch their circuit board. You can point at their circuit board. You say, that wire looks bogus, but you don't touch it. That's their job. You don't touch their keyboard. You don't touch their mouse. As soon as you say, here, I'll show you, and grab it, now you're violating academic integrity in my mind. So you talk all you want. When it comes to writing out the code or building the circuit, that's got to be under academic integrity. Okay? That makes sense? If you have any doubt, ask me. In 4760, I came up with a bunch of examples and put them in the policy page, and I will probably do that here too. We're looking at a bad flu season this year. If you're sick, don't come to class. Don't come to lab. We're sharing keyboards. We're sharing mice. You're sick. Everybody's going to get sick. I don't want to get sick. I had the big flu shot. I had the over 65 flu shot, you know, the one that makes your arm swell up. But it's only 60% effective because, as you know, there are type A and type B influenzas. Any given flu season includes a vaccine with 2 type A and 1 type B. This year, there's a type B that was not included in the vaccine. It's making about 30 or 40% of the flu cases. There's also a norovirus going on. You know what a norovirus does to you? Do you know? Exactly. Don't come to class if you're barfing. I don't think you would anyway. Actually, it does the upper GI and the lower GI. But I'll let it go at that. It's about 24 to 48 hours of uncomfortableness. So, don't come to class if you're sick. Don't come to lab if you're sick. Email me. We'll be happy to make up time on that. Use the sanitizer in the hall. I've got alcohol sanitizer in the lab. Let's practice safe computing. There's some directions on how to write a lab report. Ignore the part on the final paper because we're going to change that. As you probably noticed, none of you can register for this class without the pin. So what I'm going to do at the end of class is to pass this around. Some of the pins are 6 digits, some are 5, and some are 3, which suggests to me that Excel is very bad at leading zeros. So if it's a 5-digit number, you're probably going to want to put a 0 in front of it or just not use it. I'll pass this around. What you're going to do is take the first number, write it down, and then scratch it out. You'll take the second number, write it down, scratch it out. Each number is useful for one person. Any questions about the logistics?
I have a question about prerequisites. How important is the degree to have other experience with integrated circuit?
Well, so the 315 is there for the circuit building experience. And if you've built circuits other places, that's fine.
So like, do you know about NP 363?
Taught by Earl Kirkland. I think that should be fine. I think that's, you do quite a lot with op amps in there, if I remember right, and filter topologies, and yeah, that's fine. Any other questions? There's a few enough people, y'all get in. So just go through and, how many people are ECE MEng? Again, let me see, show of hands. Most people. How many people are undergraduates? 3 or 4. Okay. We're going to give you all access to the 238 lab. So you'll be able to go in there anytime. The next lecture, I'll bring a sign-up sheet. In the next lecture, I will need your name and your ID card number. Not your net ID, but your ID card number to activate the door. And then you'll be able to go in anytime and work, which is nice. It's a blessing and a curse. But as usual, this is not an invitation for you to have your friends work in there with you. So we'll give you the safety lecture and the I've got to give you a safety lecture if you work in there by yourself. Don't drop the oscilloscopes on your foot. Don't put the soldering iron up your nose. You laugh. I did that once when I was 12. I had one of the old time with the trigger, you know, the big old soldering guns with the trigger, and I was holding something in this hand, and my nose started itching. I took this thing and went and rammed it right up my nose. It smelled bad. It didn't actually hurt because all it did was boil snot. The same reason you can walk on coals, right? So don't do that at home. But I have to give you the safety lecture so that you can work in there by yourself and be safe. So we have, at this point, we have 12:55. We got 30 minutes. So again, anything on logistics. It's going to be about 4 labs plus a final project and a web page at the end. You're going to document this on a web page. Nish. First lab will start next week, not this week. This lab, by the way, is going to meet in 238 Phillips, not where it said in 403. I don't know what 403 is, whether it's a lab or what. It's a classroom, right? So we're going to meet in 238 Phillips, either Thursday or Friday afternoon. How many people would go on Thursday? How many on Friday? Oh, baby. Okay. Here's how it is. I've got 2 classes, 5760 and 5030. They're both meeting in there on Thursday and Friday. So, I'm going to be multiplexed. The TAs are going to be insane. Actually, the TAs will only be on one course, not both courses, unless you want to do something really crazy. If, if it gets to be too much of a load, I may be able to get one more TA ship to help smooth things out. However, because you're allowed to be in there anytime you want, you don't necessarily have to work during lab periods. You do have to come in and demo during your lab period. You have to show me the circuit during your lab period because I'm not going to be there all night. But you need to come in and show me you need to show up at least once a week for lab, check in with the TA, check in with me, let us know what's happening. But we'll be able to tell whether you're working or not. For the first couple of weeks, we'd like to see you there during labs. As the semester goes on and during final project time, it's become more freeform. Okay? That answer? Anything else? With an MEng class, we have a lot more freedom about opening the lab for you. Okay, well, let's do a little bit of biology since probably this is a little bit rusty in your mind. As you know, I hope you know, that all animals are made up of a collection of cells. A cell is some sort of bounded elementary unit of biological reproduction. It has a nucleus. Every cell in your body has a nucleus, has a cell membrane, various other things. Mitochondrion produces energy. But what we're going to be particularly interested in is the cell membrane, because it is the impedance barrier, it is the electrical impedance barrier between the inside of the cell and the outside of the cell. And so this is where most of the voltage occurs that we're going to be worried about measuring, theoretically modeling, and so on. There are some other electrical effects. For instance, mitochondrion keeps a huge hydrogen ion gradient across its membrane, which acts as a fuel cell to, there's a several dozen millivolt gradient across here, which the hydrogen ions produce and which is used to drive a reaction to build ATP, to power the cell. Are these words familiar from someplace in your... Yeah, it's sort of like adenosine triphosphate. Yeah, this is kind of like Scientific American level biology, right?
But do the dead cell, okay, the skin is made up of dead cells?
Skin is, the outer layer of your skin are dead cells, right? It's kind of like just the husk of this thing, and there's no real reproductive apparatus in it. Go down one level, and there are cells that are being generated continuously.
But then, will the dead cells also have the same biology? I mean,
They don't have much biology at all. They're meant to be a disposable layer. Manesh?
yeah,
Oh no, they don't have the same electrical impedance. They act much more like a pure capacitance. We'll talk about this in some detail. So the cell membrane, if we were to now blow up this little section here and look at the cell membrane, the thickness of this is about 7.5 nanometers or so. It's made of fatty stuff, so-called phospholipids, that have a head on them that are attracted to water and a tail which is attracted to fat. So this is a self-organizing lipid bilayer that is a very, very good insulator. It has an extremely high resistance. As you all, I don't know if you've ever stuck an ohm meter into Wesson oil or into corn oil or anything like that, but you know, it's like infinite impedance, right? Oils are very high impedance. So So this is an insulating layer, except that at various places along the membrane, there are protein channels which go through the membrane that allow various items to flow in and out, including ions. These are therefore called ionic channels, or just channels sometimes. Some of them are quite specific. For instance, there is a channel that only allows sodium to go through. There is a channel that only allows potassium to go through. There's a channel that allows any positive ion to go through. There are various kinds of channels. In fact, on your cells, there are something like 25 different kinds of potassium channels, each with a slightly different dependency on how it allows potassium to go through the cell membrane, which can be voltage dependent or chemical dependent.
Why sodium potassium have variability?
I will tell you in a few minutes. These then act as resistors. So if we were to come up with an elementary model of this membrane, at the very least, it's going to have to be modeled as a capacitor in parallel with some variable nonlinear resistor. And we'll talk more about that too. So if we were to take a sort of a typical mammalian cell and look at it, then externally we have sodium ions at about 120 millimolar. Remember molar? Moles per liter. Chemistry. Yeah. Potassium outside is at about 5 millimolar. Chloride minus is about 125. It better add up. There's some random anions, positively or negatively charged, or in this case negatively charged proteins, which outside the cell are approximately 0 concentration. And calcium is at around 1 millimolar. And by the way, is extremely well regulated. Inside the cell, internal to the cell, potassium is at about 12, about an order of magnitude lower. Calcium is at about 125. Potassium is 125. Chloride is around 5. Charged proteins and various other negative ions are around 108 millimolar. And calcium is about 10 to the minus 4 millimolar. As it transpires, internal calcium is a signal for various events to occur in the cell. For instance, in muscle, a calcium pulse causes mechanical contraction. In a nerve cell, a calcium pulse causes release of various chemicals into the external environment. So calcium is a signal, and because of that, it is extremely well regulated inside the cell, because you don't want random muscle contractions, for instance, going on. That would be bad. Any questions so far? Now, the reason for bringing this up is that these gradients, particularly sodium potassium, when combined with an ion-specific channel, so if you have a channel which only allows sodium to go through, then a gradient plus the channel implies a battery. All right? It's a chemical battery. if you just have most cells, if you have most cells just sitting here, then the cell is somewhat permeable. Permeable, I can't spell at all. EA, permeable to potassium plus, and not very much to chloride minus, sodium plus, or the negative ions, which are rather big. Since it is permeable to potassium, and there's a lot of potassium internally, well, let's just say that you start this at rest here with, so now we have internal here, external here. We have a lot of calcium over here, potassium over here, a little bit of potassium over here. There's no voltage across this membrane. You open up a channel through which potassium can flow. Fick's law, remember Fick's law? Fick's law says that the diffusion is proportional to the concentration gradient. You're going to start to have potassium diffuse down this gradient. There's a chemical drive, or put it more thermodynamically, the probability of potassium going this way is greater than the probability of potassium going this way, and so potassium flows this way. Every time a potassium leaves, you have one negative net negative charge now on this side because the anions and the chloride are not leaving, right? So every one that leaves adds another negative charge. Oh, but potassium is positively charged, and so sooner or later it's going to get harder and harder for these potassiums to leave because they're being attracted back through this channel by the negative ions left behind. And so the system is going to come to equilibrium, at which point there'll be no net flux, no net flux of potassium, and it'll come to equilibrium at some negative voltage inside the cell. And of course, since the membrane is a capacitor after all, and there's negative charges on the inside, there'll be certainly positive charges stuck to it on the outside also, but they won't be able to go through the membrane. They're just stuck there. So this is kind of like an electrolytic capacitor. It is exactly an electrolytic capacitor. So, given that most cells are permeable to potassium, most cells will have a potential. All cells, in fact, will have a potential if they're just sitting there. If you get rid of that potential, the cell is dead. That potential is a diagnostic of the health of the cell. Now, what we're going to find is that for certain specialized cells, most of the cells in your nervous system can manipulate the permeabilities to potassium and sodium and therefore change the voltage. And as they do that, they can use voltage as a signal. All right, so the cell, as we're going to find out over the next lecture or so, that the way cells are going to signal is that they're going to manipulate the ratio of permeabilities of sodium and potassium and thereby change a voltage which becomes a long-distance signal. These changing voltages are also present in muscle cells. There's a voltage pulse which causes the calcium pulse, which causes the contraction. They are, where else are they? Anybody else know any place? You see voltage changes in cells? Neurons. What else? Light receptors in your eyes. Yeah. Smell. All kinds of receptors have a voltage change. So your ears have a voltage change which is mechanically driven. Your nose has a voltage change which is chemical receptor driven. Your eyes have a voltage change which is driven by isomerization of a light sensitive chemical. But there's other places too. Go ahead. Goosebumps are muscles in your skin that cause your hairs to stand on end. And you might think that if your hair stands on end, you get better insulation, if you have any hair at all. And so goosebumps helps it gives you a better insulation layer. There's also a thing called sympathetic activation, which is caused by adrenaline or adrenaline-like materials, which causes a lot of smooth muscle to contract, and that makes your hair stand up, which is related to fear response. There's a set of cells in just above your kidneys, in the medulla of your kidneys, which secretes noradrenaline, adrenaline. It's involved in fight, flight response, which are electrically active. There's all kinds of electrically active. A lot of cells that secrete chemicals in your body, in your stomach, the acid secreting cells are all electrically active. So the ability to manipulate permeabilities as a function of chemical environment, time, and voltage is key to understanding what's going on in the nervous system. We're not going to go into that a lot, except to ask, how big are these changes? How fast are they? What are their impedance? That'll give us the information we need to record them effectively at the surface of the animal, or at least at the surface of the cell, depending on how invasive we want to be. Since we're going to be mostly working on humans, we're not going to be sticking electrodes into you, which means we're going to be asking, if we get a 100 millivolt change at the surface of a cell, what will be the change of voltage at the surface of your skin? And that's going to require a coupling model to go from the cell to the skin, and we're going to go through that. So any questions about this? So you can write a, if we say that this is going to come to equilibrium, then the flux is going to be zero. We have two fluxes, one of which is determined by Fick's law, diffusion down the gradient, and the other one, which is determined by Ohm's law, which is diffusion along a voltage gradient. And at equilibrium, those have to be equal. So we can write a flux equation, which is the diffusion constant and the gradient of the this direction being now x. The flux is given by some diffusion constant times the gradient of the concentration. That's Fick's law. And Ohm's law where this is the same diffusion constant, this is the solute concentration, and the reason that that appears as concentration is the number of particles determines the more particles you have, the higher the conductivity. And K is a strange constant. K is equal to ZF over RT. Z is the charge in electron units. So for potassium, this equals 1. F is Faraday's constant. That's the number of coulombs in a mole. Number of coulombs in a mole, it's 96,000 something, 500 or something, right? Something like that. So this has a value of like 96,000 more or less. RT is the usual gas constant in the absolute temperature. So probably I could assign that you integrate this, and you probably could. Depending on how long it's been since you took calculus. But what we're going to do is, to solve this fairly quickly, is at equilibrium we set this equal to 0, of course. At equilibrium, flux has got to be 0. Divide both sides by S. And divide out D. The only thing we have to be careful about is that this only works, of course, if S is non-zero everywhere. And so we'll have to make sure that we don't make that blunder. But as long as we have finite concentrations everywhere, this is a valid manipulation. Then we can rearrange this as thank you. dv dx k dv dx is equal to 1 over s ds dx. And we can rearrange this to here, yeah. And we can rearrange this to dv is equal to 1 over k ds over s. Oh, we all know how to integrate that. So if we do the integral here, we find that the V membrane, across the whole structure, is going to be equal to RT over ZF, natural log of the solute, the concentration of the solute outside over the concentration of the solute inside. And at room temperature for potassium, T equals 20 degrees C. Of course, that's not where your body operates, but that's where squid axons operate in the dish. At 20 degrees C, and for potassium, this turns out that Vm is going to be equal to 58 millivolts times the log base 10, because people like to think in log base 10 quite often in biology, times K out over K in. For these ratios, we get about 81 millivolts. Vm for this, Vm is going to be about minus 81 millivolts. So if you were to take a microelectrode, by the way, as an aside, you can take a glass tube, you can take a 1 millimeter diameter glass tube, put it in flame, pull it out and stretch it. And you can stretch it down below a wavelength of light in diameter and it will still be a tube. It won't pinch off. So that you can make extremely fine electrodes. I used to do this for a living. You can build electrodes that have a opening diameter at the end of on the order of 400 nanometers or 200 nanometers. You can take one of those and you can push it right into your finger and it just goes until it breaks off. Then it stings. I've done that. But it's so sharp, you could put it into a single cell. You can slide it right through the membrane, if you're lucky. You get practice. You can slide it right through the membrane into the cell, and you can measure the potential. So if you put an amplifier on here, you can measure that, and if you set the reference voltage to 0 outside the cell, just outside the cell, as you push the electrode into the cell, you'll record, for these concentrations, about minus 80 millivolts. Quite a large signal, really. If you damage the cell enough with the electrode that the voltage drops, the cell is dead. It needs that potential. It produces the potential, and it needs the potential, otherwise it's dead.
So basically in electric shock, you are changing the gradient of all cells?
So if you get macroscopically shocked, there's lots of effects. One is brute force heating of your body. If you get a large amount of current through your body, you get ohmic heating, and that can cook you. You don't have to cook very much for you to be in deep trouble if it goes through your heart. The other thing that can happen is that cells that respond to electric field, like your muscles, will lock on and not let go, which includes your heart. So you can stop your heart with a big enough electric field. If you take a shock through your nervous system, through your central nervous system, it does all manner of changes and damage. It depolarizes cells. If the gradient is big enough, it depolarizes cells. What I haven't said yet is that there is a nonlinear amplifier in the cells. And if you trigger the nonlinear amplifier, if you make a big enough voltage change to trigger the nonlinear amplifier, then you get runaway depolarization, which resets itself, but you can cause every brain in your cell, every cell in your brain to fire simultaneously. That's bad. So there's lots of ways in which external electric shock is bad for you. Next topic is, first of all, is going to be how does this change? And we're going to find that the ratio of the conductances changes. And then how much of this change can we record on the surface of the animal? Because you have, so we have to know, is it a monopole? Is it a dipole? What is it that's propagating? What is it that's being produced? Well, turns out, the short story is it's a dipole, and the field drops off as the, from a dipole, how does the field drop off? Who remembers that? From a monopole, field drops off as inverse square. 1 over r cubed. It's always a guess. If you increase the, that's a good guess, because if you increase the strength of the multipole, increase the size of the multipole by 1, you lose a field strength of 1. Yes, exactly. It's a multipole expansion. And so the field strength drops off rather rapidly from the cell. So if you expect to get a big change at the surface of the animal, you need a lot of cells close to the surface, like bicep. Much harder to do. Bicep is going to produce something like 100 millivolts of change at the surface. You can just about record it with a voltmeter. Your brain activity is going to produce something like a microvolt of change at the surface of your head, because the set of cells that are changing voltage are smaller, and your skull's pretty thick. Better be. For protection. So we need to talk about this kind of stuff, how these things change, and then how the changes are affected by the environment that the cells are in. And then we're going to start talking about electronics. Go look at the 50/30 page, figure out what you have to read, maybe look at the textbook, start reading the textbook. Get ready for the first lab a week from the end of this week. Oh! Take a pin, scratch it off.